All right, so hi everybody. My name is Andrew Bunner, and like I said, I work at Google DeepMind on their generative multimodal models. For the past 8 years, most of the time I spent in kind of classic computer vision work, so teaching computers to recognize pictures. But 2 years ago, I switched over to teaching the computers to draw completely new pictures. And this is a cat armadillo, courtesy of Google's Imagen 2 model. So I just want to do a quick pulse check on where we are in the AI hype cycle before I get into the weeds here. So at the top is Goldman Sachs saying that basically getting bearish on AI. And at the bottom is a Twitter influencer lamenting the fact that humans will never have to learn to do things anymore, and it's all pointless because AI is going to do it all. And I do think that AI is overhyped in some circles, but it's also true that it's underhyped. It's really a new thing that computers can do these kinds of natural language problems, tasks that would take like an average, pretty smart human, like minutes of thinking time to do, the computer can now do in seconds. And that's really new. So I'm excited about that. I think it's going to be a good tailwind to productivity. All right, so I'm going to talk a little bit about how the LLMs work. So just kind of bear with me for this next slide, but it's going to make the rest of the talk make more sense. So here we go. Okay, on the right side here is a picture from the Attention is All You Need paper. This is the Transformer network, and it's kind of the building block of modern LLMs. And so your prompt or the context goes in at the bottom, and the top, it outputs probabilities for what it thinks the next token is going to be. A token is kind of like a word. I'm going to use the two interchangeably here. And inside each of these colored boxes are giant matrices of floating point numbers. Okay, we call those the weights of the model or the parameters. And at the beginning of model training, the model outputs nonsense, and the weights in those matrices are meaningless. And so the way we fix that is we're going to show it lots of training examples. And that's like this one on the left here. And the way training works is you take the training example and you mask out the last n tokens, you hide them. And then you ask the model, look at these first few tokens and then try to predict the first masked out token. Try to guess what that is. And then the model will do that. And since you know what word you redacted, you know what the right answer is, you can kind of nudge it a little bit, away from the wrong answer and towards the right answer. And we call that gradient descent. And what we're doing is we're sort of looking at the slope of this very complicated curve and deciding, do we make this weight like a little bit bigger or a little bit smaller in order to increase the odds we get the right answer out on the other side. And then we do that billions of times. So that's model training. And what's sort of happening during that is that over time, the weights in those matrices are coming to represent a compressed version of the knowledge that the model saw during training. And it's a lossy compression. And I'm going to explain that here. This is important. So if you take a model like Llama 3.1, it's 405 billion parameters. If we assume like 16-bit floating point numbers, that means that it can hold about 200 gigabytes of knowledge in those weights. That's way less than the training data that it saw. And so it's got to compress it somehow. And it's compressing it so much that it's going to forget some of the details. And so that's kind of a source of like why models can get things wrong sometimes. And I drew a red box around the word probabilities at the top because it's not outputting like a definitely true factual answer. It's outputting what word it thinks probably comes next. And that's in contrast to an information retrieval system like search, where it's like finding a real document that is like an actual thing and returning it. Here it's kind of making stuff up, which is still really useful. We'll talk about that. But that's, I'm kind of hinting at like why things can go wrong. And I'm going to show you a couple examples of like how things can go wrong. And then we'll talk about how we can apply LLMs and sort of improve the odds we get the right answer. Okay, so if you've used any of these models, you've probably seen this light gray text at the bottom. And what OpenAI is calling mistakes, in the industry, we call those hallucinations. A hallucination is when the model is just like making stuff up. And it's important to know that they can do that. And so this is an unfortunate case where well, it's a real court case where the lawyer used ChatGPT to help him write this brief. And in the brief, ChatGPT cited 6 completely made-up court cases. And this guy then submitted it to the judge. He did not read that fine print at the bottom. Very unfortunate. Okay, here's another failure case, a little more innocuous, trying to draw ASCII art of a cat. Nope, missed it. That is not a cat. Or just wrong number of legs. I don't know. And this is my own failure case. I uploaded here this fantasy map, and I asked ChatGPT, how do you get from the town in point A over to the castle at point B? The right answer is the blue line that I drew. And the red answer is what ChatGPT would have our heroes do, just off into the southern lands and then, way, way back. It just wasn't good at this kind of thing. And yeah, side quest, exactly. So credit to Anthropic. Claude actually did pretty well on this, so that was impressive. Okay, so how do we make the models do better? And there's this. This is a Reddit user who dug up the system prompt for Apple's forthcoming Apple Intelligence feature, and I just want to say I don't think this is going to work. Okay, so what are some better strategies? This is really the most important thing. So your engineering team or anyone who's really trying to apply these for a real problem, you have to make an evaluation set. This is the biggest font I could fit on the slide. You want a whole suite of test cases where kind of what the right answer looks like, and then as you're fiddling around and trying different things, you can see hey, is it getting more things right or more things wrong than the last time? All right, so let's talk about what you can do, what the fiddling around actually kind of looks like. So this is Paige Bailey. She's a developer advocate for Google's cloud AI offerings. And she's kind of outlining this hierarchy of things that you should try, starting with the bottom of this pyramid here, prompting, basically prompt engineering. So you change the prompt a little bit, try a few different things and see how does that change the metrics on your evaluation set. And some of that is straightforward things like giving the model really clear instructions, giving examples of hey, for this response, or for this question, this is a good response. We call that few-shot prompting. But sometimes weird stuff works, like threatening the model. That sometimes improves accuracy. Bribing it, that also helps sometimes. So it's kind of a strange world we're in right now. If we move up this pyramid of difficulty, the next thing is retrieval augmented generation. And that's when you can use some information retrieval system to look at the problem that you're given and then find reference material that probably has the right answer inside of it. And then you stuff that in the context window. And that helps a lot. That is really great bang for the buck. And examples of those retrieval systems are things like these vector databases now, or just a classic search thing too. All right, moving up the ladder, or the pyramid, I guess, we come to sort of small scale fine tuning. So this is low rank adaptation, parameter efficient tuning. This is when you're not tuning the weights, the entire model, but you're tuning just some of the weights. And this has some trade-offs. You're going to incur some extra serving costs because you're now serving a little bit of a custom model with these custom weights here. But the real cost here is coming up with the training examples that you're going to fine tune on. That's actually where the work is here. And then if you go all the way up, full scale fine tuning the entire model, this has even higher serving costs because now all of the weights of the model are your own weights. They're custom, different from the base model. And again, you have to come up with the fine tuning examples. But it works really, really well. Okay, so this is a paper that some Googlers published basically about retrieval augmented generation and how it was kind of the best strategy short of fine tuning to have the model get the right answer. I'm going to skip the details here, but just trust me, it worked really well. Okay, I'm gonna skip some of the details here. This is a paper I was involved with called Image and Words, and I normally steer people away from fine tuning because it is just so much work. In this case, man, it worked really, really well. We had a very small model that was much worse than GPT-4 at the task of image captioning. We took about 10,000 really, really good fine-tuning examples And with that, we were able to be competitive with a much, much larger model. So it's pretty impressive results. Okay, this is my former manager on LinkedIn, and I really like this post because he's saying exactly what it takes to fine-tune one of these models. And it's $70 of compute and 14,000 fine-tuning examples, which is, again, that's where the real energy and time and cost is going to go into. That's a one-time thing. Yeah, one-time thing. Yep. Okay, so I'm going to talk a little bit about the cost of serving these models, and I think this is going to be some good news. So this is a screenshot I took from the site artificialanalysis.ai of the pricing of different models. And what's really incredible to me is that the models on the far left, which are literally 100 times cheaper than the models on the far right, are almost as good. So that's really amazing. And the company that does this, they keep having to rescale the y-axis because the cost of these models keeps dropping. So it's really incredible. What a time to be alive. And I took that screenshot 2 weeks ago. It's already out of date. Since I took it, both OpenAI and Google have reduced the cost of their models. And that's not actually a new thing. Between January 2023 and March 2024, OpenAI reduced their price twice by 50% both times. And then again, most recently.
This might be just basic education for me. What's the difference between input cost, output cost? How are you defining that?
So the questions about the difference between input cost and output cost. Input cost is how long your prompt is. That's the input, and that's cheaper than the output tokens. Yep. Okay, yeah. So lots going on the cost side. I think that some of this progress is a combination. So some of it is modeling advances. So we're using really big smart models to get really great training examples to teach smaller, cheaper models how to be smart. So that's one source of cost savings. Another is quantization, where we use lower precision floating point numbers, which are faster to work with. But there's another thing driving the cost down that I think is going to matter in the future, and that is hardware innovation. And we are in a Cambrian explosion of innovation on the silicon side. It's crazy and exciting. On the right is this chip from a company called Cerebras. That chip is 56 times larger physically than the NVIDIA H100. It's absolutely massive. I don't know if it's going to work in the marketplace, but I think it's a really interesting direction. On the top left is another company, Grok. They've got a strategy where they use a really advanced compiler to lay out the weights of the model statically in memory, just sort of burn them into the chip, and take advantage of the fact they know that chip is going to be running just that model. And they can get a lot of speed out of that. On the bottom there, you've got the Apple M3 and then Intel's Gaudi 2 or 3 or something accelerator. And that's leading out NVIDIA. So NVIDIA is not standing still. Everyone is innovating here very quickly. And this is Paige Bailey again, predicting basically more cost drops. She says one other thing here, which I want to kind of emphasize, which is the context window. So she's predicting that eventually we're going to have an infinite context window. So right now, a context window is about maybe 2 million tokens on the flagship models from Google. That's a lot. You can stuff a whole book in there or a movie. So it's pretty amazing the amount you can stick in there. So I think it really is a game changer as that gets bigger and bigger. So it's really a great time to be an application developer, someone operating at the funnel story level, because they keep getting smarter, they keep getting faster and cheaper. Okay, so just some kind of closing thoughts. These are my own opinions here. So I'm the guy on the left. I think AI is a tool, but I work with people on the far right of this distribution who believe the same thing. And in the middle is this guy who's written 1,700 words about how AI will usher in this new world of untold destruction and mayhem, and he's freaking out. And I think he's wrong. I think that AI is progressing along a S-curve, like most technologies, where they get better quickly and then they begin to plateau. It becomes more and more work to eke out wins. And I think that as we move along that S-curve, we're still going to have kind of situations where the model like misbehaves in these naively stupid ways, like the ChatGPT with the map, where the questions you're asking are just like really outside the domain of the training distribution. But they'll get fewer and fewer of those. Like as the model providers like see those things and they realize their customers care about them, they're going to fix them. So I kind of think that AI is going to be this amazing new like tailwind of productivity for knowledge workers, for creatives, for salespeople, and I'm optimistic, and I think you should be too. And that's my talk. Thank you.